Lab 1 Constant Velocity for Physics 2211. The purpose of the lab was to observe the motion of a moving object that is moving at a constant speed and isn't changing direction. I then compared my model to my observations by plotting both the observed position versus time from the analysis of my video and the predicted position versus time. Some of the fundamental physics principles included in this lab are constant velocity, Newton's first law, and Newton's second law. Constant velocity provides that the slope of the position versus time graph is constant. Constant velocity also provides that there is no net force on the system. In the first two graphs, the velocity is constant, where in the first one it's positive and in the second one it's negative. The third graph shows a non-constant velocity as it is increasing over time, because there has to be a net force acting on the system. Newton's first law provides that an object at rest remains at rest and an object in motion remains in motion at a constant speed in a straight line unless acted on by an unbalanced force. This is showcased by the equation F net is equal to dp over dt, or the change in momentum over time, as momentum's formula is the mass times the velocity of an object. If there is no change in the velocity as the mass is constant in these systems, then there cannot be a net force acting on the system. Newton's second law provides that F is equal to ma. If there is no acceleration, then there cannot be a net force acting upon the system. My experiment consisted of a cart that was rolled on a track. The system was the cart, and the surroundings were the track and the earth, as these could have imposed forces upon my system. The initial conditions that are assumed are the velocity of 0.763 meters per second, estimated and calculated by my spreadsheet, and the net force of 0 newtons with an acceleration of 0 meters per second squared, because if there is an acceleration of 0 meters per second squared, there cannot be a net force. The assumptions that I made in the experiment was that the initial velocity was constant and there was no acceleration. Another assumption that was made is that there was no friction or air resistance and the net force was truly 0 newtons. In a real world, we do not know if this is true. In my code, I inputted 0.763 meters per second as the x component of the velocity initial of my system. The delta t is 0.03 because in tracker, that is how much time was taken in between the steps of my tracked video. In the second video, we can see that while t is less than 2.73, as my video is 2.73 seconds long, and the F net vector is 0 newtons all around because there is no net force. You can see the velocity update formula and the position update formula down below. My output involved this constant velocity graph of position versus time. We can see that this velocity is constant, as in the second graph it shows a straight line for the velocity versus time graph. This also shows that the velocity is not changing, which means that there is no net force on the system. Here's a sample picture from my tracker calculations. There's also some data that was imported from the tracker, and it shows how the position is changing compared to the time. Here is a picture of the experimental data versus the computational model. The blue line is the experimental data, and the red line is the computational model. We can see that at the start of the time, the blue line and the red line are relatively close together, but as time goes on, the gap between these lines increases. This shows that the error is exponentially compounding over time and causing a larger gap in between these lines. Some reasons for this error can be shown in the next slide. Possible sources of error are non-constant velocity, meaning that there were forces from the surroundings acting upon the system. This could either be at the start when the cart was pushed, there was an acceleration, and other forces could be friction from the track or even air resistance from the surroundings. Some questions to discuss are: if the axes were flipped, the data would be reflected across the x-axis, so the directions of the position and velocity would go from positive to negative, but the magnitude of the position and velocity would still remain the same. It is not possible to say or determine how many other forces are added together to give a zero net force, because other than the force of gravity and normal force, we can't know that the other forces are canceling out. Thank you.